we can try to get an expression for alpha n plus 1 over alpha n in terms of alpha plus 1 over alpha, but that makes very big expression, so it's very simple for square and the cube, but it becomes very large. And then if you rewrite this in terms of alpha plus 1 over alpha, so you can use some binomial expansion and get some expression, rewrite this in different term and then show that it's an integer. However, if you go with induction, that's very straightforward. So if this is true, so it's given that already that's true, so you can we can do the step. So this is if you assume the base of the induction, when n is 1, it's already alpha plus 1 over alpha is integer. So we want to prove for higher values of n. So let's assume that it's true for n is equal to k and prove that n is equal to k plus 1. So which means alpha to the power k plus 1 over alpha k is an integer. So, if I just multiply these two numbers and alpha k plus 1 over alpha k, the product of two integers, from this one we know that this is integer and then this one is integer. Product of these two integers is a still integer number. So if I open the parentheses, this expression is going to be alpha k plus 1, and if I multiply the second terms, I get 1 over alpha k plus 1, and then second part is the first and the second, so I get alpha k minus 1 plus 1 over alpha k minus 1. This number is an integer number. So now the question is, if this part of the expression is integer, then this part is also integer. So here we don't have alpha to the power k, but we have alpha to the power k minus 1, but we started with alpha to the power k. So here in this case we can use the form of the induction, which usually called generalized induction. The assumption goes like this. It's not assumption when n is equal to k, we prove n is equal to k plus 1. Instead of this very small difference, we can assume that when n is equal to k or less, the assumption is the statement is correct for all numbers equal to or less than k. Then we want to prove that k plus 1. So we have block of true statements, and the next statement is also correct. So which means we use two statements, alpha k and alpha k plus 1 is correct, and then alpha k minus 1 and 1 over alpha k minus 1 is also correct. Then using these two, we can claim that alpha k plus 1 or plus 1 over alpha k plus 1 is also correct. But for the base of this expression, we need at least two correct statements. So in order to be able to start the induction, we need at least two. So we already know that for n is equal to 1, it's correct, right? So what about n is equal to 2? So if I do the square of 1 plus 1 over alpha square, this is integer, and then that's plus alpha square plus 2 if I open the parentheses. Since this part is integer, alpha square plus 1 over alpha square is also integer. So basically I can when the statement is correct for n is equal to 1 and 2, And these two, using these two, you can multiply alpha square and just alpha and get the expression for n is equal to 3. Then since you have n is equal to 2 and n is equal to 3 is correct, using these two you can prove that n is equal to 4. And using 3 and 4 you prove 5 and so on. So the rest is the step of the induction and it's correct for all n. So this form of the induction is more general, and then you can use more terms before k, not only k.